Let's say we have a tube and we want to measure its length, but we are unable for some reason to measure the length in one step. So we have, let's say, someone measure this length here, and then someone else measure from here to here. The idea being that we're going to add these two lengths to determine then the length of the tube. So say one experimenter measures this length and gets 13.52 plus or minus 0.01 centimeters. So he's sure about the 5 but not this 2 here. Someone else measures this section to be 6.36 plus or minus 0.04. And so obviously if we want to know the total length of the tube, we simply add these nominal values, which gives us 19.88. But what is the degree of our uncertainty in this value? By how much could it be off? Whenever we add values, we look for the associated absolute errors and we add those errors. So 0.01 plus 0.04 gives us 0.05. Let's take a look at what's happening with the relative errors. To get the relative error associated with this measurement, we divide 0.01 by 13.52 and multiply it by 100 to express it as a percentage. So we get 0.074% here. And we do something similar here and we get 0.629%. Let's look at the relative error in the total length of the tube. If we divide 0.05 by 19.88 and multiply it by 100, we get 0.252. Obviously, this is not equal to the sum of these two. The sum of these two would give us 0.7 more or less. So whenever you're going to add values and you want to know the maximum possible error in the result, you add the absolute errors in your original values. You do not add these. So these percentage errors do not add up to this percentage error. These absolute errors, however, do add up to this absolute error. So let's get that very clear. So here we have the rule. Whenever we add measured values, the associated absolute errors are added up to give the absolute error in the sum. So let's look at subtraction now. In this case, we know the length of the tube and we know the length of this section, and we want to then use that information to be able to calculate the length L2 of this section here. So obviously we're going to say L minus L1. So once again we subtract the nominal values. We say 25.36 minus 24.81. That gives us 0.55. Since this is subtraction, we need to once again add the absolute errors. So 0.02 and 0.05 gives us 0.07 centimeters. Let's look now at the relative errors. So the relative error here is going to be 0.079% and here it's going to be 0.2%. Notice here in the result, however, 0.07 divided by 0.55, well, that gives us a relative error of 12.7%. So this is very notable. Whenever you're subtracting, because the absolute errors still add up, you find out that your relative error will increase significantly. So it's quite possible to have a relative error above 100%, in which case, for example, if L1 were a lot bigger and L2 were very, very small, it's quite possible that this number could be bigger than this one, in which case then your relative error would be over 100%. Subtraction is something you have to be very careful with then. Once again, we notice that if we add these, we definitely do not get 12%. So whenever you add or subtract, you add the absolute errors in your terms to get the absolute error in the result. So recapping, whenever we subtract measured values, the associated absolute errors are added up to give the absolute error of the difference. And so we can summarize for both addition and subtraction and say, whenever we add or subtract measured values, the associated absolute errors are added up to give the absolute error of the result. So let's look at multiplication and division now.